Hello everyone and welcome to the next video in the series. In this video I will be talking about direct proportion problems with application to chemical reactions. And we'll begin with some maybe background material and talk about atoms, molecules and also chemical reactions. And to begin, atoms, these are, as we discussed in an earlier video, these are the basic building blocks of matter. You can think of atoms as Lego pieces, and just as you can put Lego pieces together to create complex structures, you can do the same with atoms. You can combine them in different ways to come up with what we call molecules. Examples of atoms are hydrogen with symbol capital H, helium with symbol capital H followed by lowercase e, and so on. There is something around about 100 of them. And you can find all of them on a periodic table of elements. Now, the name or the symbol for an atom is either made up of one letter or two letters. And if it's one letter, it's capitalized, and if it's two letters, then the first one is capitalized and the second one is lowercase. And as I just said, if you think about atoms as Lego pieces, you can combine them in different ways to come up with different kinds of structures. And in the case of atoms, you can combine them as well in different ways, and you can create what we call molecules. So a molecule is a group of atoms that sort of stick together. And all the materials, different kinds of materials that you see around you are made up of different groupings of atoms. So as an example of that, if you group two hydrogens and one oxygen, as most people know, you end up with a molecule of water. So water, a body of water, is made up of many H2O molecules. A molecule of propane, which is what you use to barbecue with, is made up of 3 carbon atoms that are stuck together and 8 hydrogens that sort of stick around these 3 hydrogens, these 3 carbons. And we write the molecular formula as C3H8. And in all cases, the number 3 and the number 8 here, as well as 2, and also if there is nothing, that means there is a 1. So you could actually think of H2O as, let me now, I'm going to put the 1 in and then take it out. I need a 1. Okay, there we go. So H2O is in fact H2O1, and it indicates that there are 2 hydrogen atoms and 1 oxygen atom in a molecule of H2O1. Same thing for C3H8. It has 3 carbon atoms and 8 hydrogen atoms. Now again, if there is a 1, we don't write it down. So I am going to take out the 1. Okay, so H2O means H2O1. And these are molecules. Now there is a notation that we're going to use in the kinds of problems that we will be solving, and this notation puts a number on the left side of a molecular formula. So for example, 4 C3H8, and we should understand that this means 4 molecules of C3H8. So if you think of one molecule of C3H8 as a grouping of 3 carbons and 8 hydrogens that stick together, then imagine 4 of those. And that's what we are talking about. Sometimes people might think that 4 C3H8 means that you have 4 C3s, and then to that you add 8 hydrogens, which is not the case. It's 4 molecules of C3H8, so all of it is repeated 4 times. And if that's the case, then we can of course multiply 4 by 3 to find the total number of carbon atoms in 4 molecules of C3H8. Because if one molecule has 3 carbons, and you have 4 molecules, then in total you will have 4 times 3 or 12 carbon atoms. And same thing for hydrogen. If one molecule has 8 hydrogens and you have 4 molecules, then in total you will have 4 times 8 or 32 hydrogen atoms. This is important because when we work with chemical reactions, we will always talk about so many molecules of C3H8 or so many molecules of H2O. And it should be clear to everyone that this means 4 of the molecule that follows and to find the total number of atoms, you can multiply 4 by the subscript here to find the total number of carbon atoms, and 4 by 8 to find the total number of hydrogen atoms. Okay, so with that background, now let's talk about changes, because when we talk about a chemical reaction, we would like to be very clear as to what constitutes a chemical reaction. And there are, broadly speaking anyway, there are 3 kinds of changes that we observe. The first one is a physical change, and this is a process in which there is no change in molecules or atoms, although some kind of a change is observed. An example of that is when ice melts, and so H2O solid becomes H2O liquid. And when ice melts, the groupings of atoms in molecules of water do not change. They still stay as H2O. However, we do observe changes in that the solid state starts to flow. But the reason for that is because flowing, going from a state of solid to a state of liquid, has to do with how fast the molecules within the body move. And the warmer an object, broadly speaking, the warmer an object, usually that means that the faster its molecules move around and about. And if an object is heated to a high enough temperature, then its molecules start to move at such higher speeds that the intermolecular forces will not be able to hold them together in a rigid solid state, and the material starts to flow. And so this has nothing to do with the structure of molecules. Molecules are still the same. It's just about how fast they move around and about. And therefore, these are physical changes. There is no change to molecules. There is no change to atoms. We started with 2 hydrogen atoms. We end with 2 hydrogen atoms. We started with 1 oxygen atom, and we end with 1 oxygen atom. Okay, a chemical change is a process in which there are changes in molecules, but not atoms. So atoms still stay what they are. An example of this is when you burn propane, and that generates CO2 and H2O, and heat, of course, and we use the heat to barbecue with, let's say. So C3H8 combines with oxygen to generate carbon dioxide and water. That's the way you make sense of this. And of course, because you can see that molecules changed. We had groupings of C3H8 and 2 oxygen atoms in O2. And now we have groupings between 1 carbon and 2 oxygens, and groupings of 2 hydrogens and 1 oxygen. So the molecules changed, and the substances, materials changed. You can see that we start with propane and oxygen, and we end up with totally different kinds of materials, CO2 and H2O. And in fact, that's how different kinds of materials differ from each other. Their molecules are different. Okay, so as it stands though, it doesn't seem like atoms have not changed. We said that molecules do change, but atoms do not change in a chemical change. And it seems like atoms did change though, because we start with 3 carbon atoms and we end with only 1. So we cannot account for 2 carbon atoms. And we started with 8 hydrogens and we now have only 2. And while we started with 2 oxygens, now we have 2 here, and we have 1 there, for a total of 3. So it appears that 1 oxygen appeared from nowhere. And so in order for this not to happen, we have to realize that it's not really 1 molecule of C3H8 that combines with 1 molecule of O2 to generate 1 molecule of CO2 and 1 molecule of H2O. If we try to balance the reaction, and that means making sure that the number of carbons on the left side of the arrow equal to the number of carbon atoms on the right. So we balance the carbon atoms, and then we balance the number of hydrogen atoms, and so on with oxygen. Then we would find that we would have to have this kind of a situation where 1 C3H8 combines with not 1 O2 but 5 O2s, and they generate 3 CO2s and 4 H2Os. And so if you now count the total number of carbon atoms on the left, we have 1 times 3 for a total of 3 carbon atoms, and here we have 3 times 1 for a total of 3 carbon atoms. So now we have accounted for all of the carbon atoms. For hydrogen, 1 times 8, we have 8 hydrogen atoms to begin with, and now we have 4 times 2. 4 molecules, each one has 2 hydrogens, for a total of 8. And so no hydrogens have been destroyed and no hydrogens have been created. For oxygen, we have 10 on the left, that's 5 times 2. On the right side, we have 3 times 2, which is 6, plus 4 times 1, which is 4. And that totals to 10. So we have accounted for all of the oxygen atoms as well. So this means that 1 molecule of C3H8 combines with 5 molecules of O2. And that generates 3 molecules of CO2 and 4 molecules of H2O. Now these red numbers, these numbers that you see, they are used in working with chemical reactions when we bring the math in to work with how much oxygen do you need, or how much water do you create. We will be using these numbers. So it's important to understand that in addition to telling us how many of each kind of molecule we need to start with and how many of each kind of molecule we end with, it's also important to understand, and here's the key to the math part, that these numbers are related through direct proportion, which means if you double any one of them, you have to double the other ones. If you multiply any one of them by 3, then you have to multiply all of them by 3. And if you divide any one of them by, let's say, 2, then you have to divide all of the rest of them by 2 as well. And the reason for this should be somewhat obvious. So if I start, let's say, with 1 molecule of C3H8, and I have enough oxygen, let's say, then I will create 3 molecules of CO2. So if I start with twice as many, 2 of these, then it does make sense that I will end up with twice as many CO2s, or 6 of those. And if I start with, let's say, 15 oxygen molecules, which is 3 times as many, then it makes sense that I will end up with 3 times as many water molecules, which is 12 of them. And same thing if you take a look at the molecules on the same side of the arrow. If I start with twice as many C3H8s, then I will need twice as many O2s, or 10 of them. And this argument works for any number, and therefore these numbers are related through direct proportion. So the methodologies that we talked about in earlier videos on everyday life problems and also conversion of units can be used here as well, and I will show you how soon enough. Another thing before we move on from this presentation is that these numbers may be thought of in the sense of individual molecules or moles of molecules. So you could also say 1 mole of C3H8 needs 5 moles of O2, and if you combine them, they will react, regroup the molecules, the atoms in the molecules will regroup, and you will end up with 3 moles of CO2 and 4 moles of H2O. Okay, now the third kind of change is nuclear change, and that's a process in which there are changes in atoms, in the nucleus of atoms, actually I should have said, in which there are changes in, let me add that on, the nucleus of atoms. Okay, so that's why it's called a nuclear change. An example of this is carbon decay. So something like C14, carbon 14 becomes N14 plus an electron. And I will talk about nuclear changes much later in the series, but for now our focus is on chemical changes. So we will be working with formulas like this. Okay, so now problem number 1, here it is. It says, consider the following chemical reaction. 1 C3H8 combines with 5 O2s, and they generate 3 CO2s and 4 H2Os. What amount of CO2 is generated if the reaction uses 16.7 moles of O2? Now remember that we said we can think of these numbers in the sense of individual molecules or moles of molecules. And in this problem, we are thinking of them in the sense of the mole. All right. So we know that we have 1 mole of C3H8, and we need 5 moles of O2. and these generate 3 moles of CO2 and 4 moles of H2O. And in this case, we are talking about O2 and CO2. So one of the things that you should do is take a look at which two molecules are we talking about. In fact, the rest of the information that's given, it doesn't matter right now. What matters is that we are talking about CO2 and O2. And this leads us to pick up the numbers 3 for CO2 and 5 for O2 and relate them. So there is one relationship that we have here, and this is that 3 moles of CO2, that's from here, correspond to 5 moles of O2, which is from here. Okay, so that's one relationship that we have. And that's pretty much all that we need for this problem, because in chemical reactions, these numbers again can be interpreted in the sense of the mole. And that's the only thing that we are dealing with in this problem. We are not dealing with grams or liters, but moles. And if you have moles, if you start with moles, you can always jump to the chemical reaction and use the numbers in the chemical reaction to start your problem. Alright, so the solution to this problem, an algebraic solution, we set n as the amount of CO2 that is generated in moles. And because there is only one relationship, then there will be one division, and we write our equation like this. So it will have this kind of a form. On the right side, we begin with the number that we want to work out, which is 16.7 moles of O2. So we write down 16.7 moles of O2. And then the numbers in the relationship, as usual, go on the top and the bottom of the division, with the one that has the same unit as moles of O2 here appearing down here. And therefore 5 moles of O2 will go down, and 3 moles of CO2 will go on top. And therefore we end up with this. Alright, as before, if you want to make sense of what's happening, why is it that this kind of a setup works, then you think of the division here. You perform that division, and that gives you 6/10 of a mole of CO2 per mole of O2. So it tells you how many moles of CO2 for 1 mole of O2. And if you multiply by the amount that you have in moles of O2, then you'll end up with total moles of CO2. And again, I would like to mention that this is very, very similar to the situation where we have now let me see, where we have something like $3.10 per pen, and then we multiply this by, let's say, 5 pence, like this, and this gives us the total amount of money. So if we know how many dollars per pen, it does make sense to multiply by the number of pens to find the total amount of money that we spent. And in that sense, it also makes sense. This is the same as dollars per pen. It's moles of CO2 per mole of O2. And again, in the same manner, we have moles of CO2 per mole of O2, and then we multiply by the amount of O2 in moles to find the total moles of CO2. Okay, so now we do the multiplications and divisions. 3 divided by 5 multiplied by 16.7, and we come up with 10.02 moles of CO2, and therefore the reaction generated 10.02 moles of CO2. Okay, everyone. Now that we've talked about how to solve the problem, let's spend a bit more time on the problem and think about the logic that goes into the solution. Normally, it would be better if you actually start with by thinking about the logic that goes into solving the problem before you list your relationships and set up your equation like this. And in this case, we always begin with what's given. In this case, it's the amount of O2 in units of moles of O2. So I'm going to make a note of that here. This is what I begin with. This is the given. And then you should know always that if you begin with moles of a substance and you want to find moles of another substance, you can always use the chemical reaction because the chemical reaction relates amounts in moles, and that's how we know that from this point we can continue by using the chemical reaction to end up with amount of another substance, which in this case is moles of CO2. Okay, so in this case the logic is pretty simple. If you start with moles, then use the reaction to find moles of another substance. Now there is also an alternative algebraic solution, and I'm going to only present it for this problem. I won't use it on subsequent problems because in the interest of time, so the video doesn't become way too long. But just so you know that you can also use a different approach, although the approach that I gave here is preferred because it can be chained and deal with chain proportion problems. Very similar to the comparison that I gave you earlier in the earlier videos on conversion of units and also everyday life problems. In any case, here also you can start your solution by setting up one division equals to another division. And then we start with a relationship here, and we put down 5 moles of O2, 3 moles of CO2. Either one can be on top and the other one down. But if you put moles of O2 on top, then over here you should also put moles of O2 on top. And now here it says that we have 16.7 moles of O2, so we put that in. And then we want to find amount of CO2 that goes on the same side as moles of CO2, so down here. Now we do a crisscross. Division on one side becomes multiplication on the other side, and we get 5 times n equals 3 times 16.7. Simplifying this, we get 5n equals 50.1, and n equals 50.1 divided by 5, which is 10.02 moles of CO2. So this is the other way of solving the problem. And so the reaction generated 10.02 moles of CO2. Okay, everyone, problem number 2. Consider the following chemical reaction, and it's the same reaction. Actually, I'll be using this reaction as an example throughout this video. This time, though, it says not what amount, but what mass of CO2 is generated if the reaction generates 15.7 moles of H2O. The molar mass of CO2 is 44.01 grams per mole. Now here we will find two relationships. One is based on the numbers that you see in the chemical reaction, of course, and the other one comes from molar mass. If there is one, for every molar mass that's present in your problem, there will be one relationship. And so we begin our solution. We set M as mass of CO2 that's generated in grams. And now for our relationships. First of all, we notice that we are talking about CO2 and H2O, and therefore we will be using the numbers 3 and 4. In specifically, 3 moles of CO2 corresponds to 4 moles of H2O. So we make a note of that. 3 moles of CO2 corresponds to 4 moles of H2O. Once again, how do I know that it's these two particular numbers that I have to pick, not 1 and 5? Because the problem is talking about CO2 and H2O. That's all I need to know. The other relationship comes from the molar mass of CO2, 44.01 grams per mole. Per means for 1. And this means that 1 mole of CO2 has a mass of 44.01 grams. And so we make a note of that as well. 44.01 grams of CO2 corresponds to 1 mole of CO2. Again, the 1 here comes from per over here. Per mole. That means for 1 mole. Okay, so we have two relationships. And our equation will look like this. Now we start with a value that we want to work out, 15.7 moles of H2O. We match the unit, moles of H2O down here, and when we take a look at our relationships, the only one that has moles of H2O is this one. So 4 goes down, 3 goes on top. 4 goes down here, 4 moles of H2O, and 3 moles of CO2 goes on top. Okay, next we have to match moles of CO2 down here, and you notice that you have 2 options. And this is why you should check off the relationship that you use, so you don't use it again. I did use 3 moles of CO2, 4 moles of H2O, the top relationship. So I'm going to check it off. So I remind myself not to use it again. And now, moles of CO2, we need to match it down here, and the option is here. 1 mole of CO2, and then on top we put down 44.01 grams of CO2. Okay, so units moles of H2O cancel out, unit moles of CO2 cancel out, and we'll end up with grams of CO2. Now, one last time, I'm going to talk about how to make sense of why is it that this kind of setup works. And for that, we make a division over here, and I'm not sure where the 3 is coming from. So let me just get rid of it. Okay, there we go. So we have 44.01 grams of CO2 per mole of CO2 times 0.75 moles of CO2 per mole of H2O times 15.7 moles of H2O. And if we multiply the right hand, then we go from moles of H2O to moles of CO2. That's using the chemical reaction. The numbers in the chemical reaction, that's this piece. So we are using the chemical reaction to relate moles of H2O to moles of CO2. And we end up with 11.775 moles of CO2. Now that we have moles of CO2, we can convert to grams of CO2 using the molar mass relationship, which is where these numbers come in. And again, we have the 3 here as well. That's pretty odd, I guess. Copy and paste. That's the culprit. There we go. I saw it. Okay, let me get rid of the 3. All right, better. And then we multiply and divide. And we get 518 grams of CO2. You notice again that every step here follows the logic dollars per pen times the number of pens. This could be dollars per pen times the number of pens. These 2 units match. And then here again, dollars per pen times the number of pens. Units match. Okay, a closing statement. The reaction generated 518 grams of CO2. Now again, let's talk about logic now that we have some familiarity with the solution. In this case, if I wanted to think about what the steps are in solving this problem, I would start with what's given, which is not the molar mass, of course. That's just the relationship, which is 15.7 moles of H2O. So moles of H2O is what I start with. And again, if I start with moles, then the chemical reaction quite likely will be used right away. Here I can relate moles of H2O to moles of CO2 using the chemical reaction. And once I have moles of CO2, I can find the mass of CO2 or grams of CO2 using the molar mass. So you see, again, going from moles of one kind to moles of a different kind, that's when the reaction comes in. That's the only time that the reaction comes in. The rest of the time, either you go from moles to grams, in which you need the molar mass that relates grams and moles, or at the beginning, if grams are given, you cannot use the reaction. You have to convert to moles first before you can use the reaction. And again, in that case, you need the molar mass. Our next example, in fact, is one where we start with grams, and you'll notice that we'll have to change it to moles, and then we can use the reaction. Okay, so let's move on to the next problem. And next we have problem number 3. Consider the following chemical reaction, same reaction. And this time I'm also putting away the color coding. At some point I have to wean you off of it, so you don't get too used to it. Just remember that the numbers in the chemical reaction will give us one relationship, and anytime there is a molar mass, we get another relationship. So for the same reaction, what amount of O2 is used if the reaction generates 57.2 grams of H2O? The molar mass of H2O is 18.016 grams per mole. Now in this case, grams of H2O are given, and you should know that you cannot use the chemical reaction right now, because chemical reactions only relate moles to moles. If you are given grams, then the grams has to be changed to moles first, and that's where the molar mass comes in. And once you have the moles of H2O, then you can relate it to amount of H2O, or moles of O2. So again, once you have converted grams of H2O to moles of H2O, then you can use the chemical reaction to relate that to moles of O2, and then that answers the question. So there will be 2 steps basically. The first one will convert grams of H2O to moles of H2O to get us ready to use the chemical reaction. The second step will relate moles of H2O to moles of O2. All right, so we begin with our perhaps our 2 relationships, and will be the amount of O2 used in moles. And our first relationship is, since we're talking about O2 and H2O, we'll pick the numbers that go with O2 and H2O. So 5 moles of O2 corresponds to 4 moles of H2O. And then from the molar mass, we get another relationship. And this one says that 18.016 grams of H2O corresponds to 1 mole of H2O. That comes from per mole. So that means for 1 mole of H2O. And now we have two relationships. Okay, our equation then will look like this. We put down the number that we want to work out, 57.2 grams of H2O on the right end. We are getting ready to convert from grams of H2O to moles of H2O. For that, we use the molar mass relationship. And you can also match the unit. If you feel lazy to think about which one to use, then you can always match the unit, of course. Grams of H2O goes down, moles of H2O goes on top. So 18.016 grams goes down, and 1 mole of H2O goes on top. And we end up with the following. Now let's check off that relationship. And now we have moles of H2O here. And now that we have moles of H2O, that's the purpose of this step. It converts grams of H2O to moles of H2O. Now that we have moles of H2O, we can use the reaction to relate that to moles of O2. And that's where the numbers from the chemical reaction come in, the 5 and the 4. And the one that has the same unit as moles of H2O goes down. That would be 4 moles of H2O, 5 moles of O2 goes on top. And now we end up with the following. Okay, so we have our equation. Now I'm not going to show you the green line where I found the unit rate by dividing 5 by 4 to find how many moles of O2 per mole of H2O to explain the logic. I hope by now you can do that on your own. And so I'm going to jump to the final answer. That would come from 5 divided by 4 times 1 divided by 18.016 times 57.2. Of course, when you make sense of the problem, you start on the right and then you go to the left, and factor by factor you make sense of what you're doing. Just in case you are interested, it's also possible to go from left to right and make sense of the multiplications that way. It's actually a very interesting exercise. And if you're interested in it, and moles are a bit not as clear as units of, let's say, length or mass, you can always try to make sense of the chains that you got from left to right by looking at the problems on conversion of units. And if you have any questions, let me know and I will tell you how to make sense of them going from left to right. But they actually have to do with the sub-expressions that I was talking about in the previous video. Alright, so we finished the multiplications and divisions. The final unit will be moles of O2. Everything else cancels out, and we get 3.97 moles of O2, and then a closing statement. So briefly taking a look at the logic again, we started with grams of H2O. That was the given information. And because we have grams of H2O, we cannot use the chemical reaction right now. For that, we need moles of H2O. So the next step would be to go from grams of H2O, and that you use the molar mass for that to find moles of H2O. Once you have moles of H2O, then you can use the chemical reaction to find moles of O2. So now we use the reaction to find moles of O2, and that was the logic. Going from right back, the first multiplication achieves step number 1, converts grams of H2O to moles of H2O. Once we have moles of H2O, then we use the numbers in the reaction. Those are the 5 and 4. To convert the unit to moles of O2. Alright, now we move on to the next problem, I believe. And problem number 4, there is a total of 8 of them today. Number 4 is the longest. Problem number 4, consider the following chemical reaction. Again, the same reaction as before. What mass of CO2 is generated if the reaction uses 57.2 grams of O2? The molar masses of CO2 and O2 are 44.01 grams per mole and 32 grams per mole respectively. Now in this case, we will end up with 3 relationships. One as usual from the chemical reaction, and then there are 2 molar masses, 44.01 grams per mole for CO2 and 32 grams per mole for O2. And for each of those we get 1 relationship. Okay, so to start off the solution, M will be the mass of CO2 that's generated. And the relationships, because we are dealing with CO2 and O2, we pick the values that go with CO2 and O2. So 3 moles of CO2 correspond to 5 moles of O2, And then from the first molar mass, 44.01 grams per mole, that's for CO2, we can get one relationship. 44.01 grams of CO2 corresponds to 1 mole of CO2. And from the next one, 32 grams per mole, we get one more relationship. 32 grams of this time O2 corresponds to 1 mole of O2. Okay, 3 relationships and therefore 3 divisions. We begin with the number that we want to work out, the 57.2 grams of O2. Now again, in this case, we need to convert from grams to moles before we can use the chemical reaction. So the molar mass of O2 comes in. Those are the numbers, 32 grams of O2 and 1 mole of O2. You can match the unit if you want. There is only one that has grams of O2, so 32 grams of O2 goes down and 1 mole of O2 goes on top. And now we have converted, we have gone from grams of O2 to moles of O2. Now that we have moles of O2, we can use the values in the chemical reaction. Those are 3 moles of CO2 and 5 moles of O2 to relate moles of O2 to moles of CO2. So let me first check off the relationship that I used. And now I need moles of O2 down here. You can find it here. So 5 moles of O2 goes down, 3 moles of CO2 goes on top. And let's check off the next one that we used. And now the last one, moles of CO2, we need that one down here, and we put down moles of CO2 down, 44.01 grams of CO2 on top. And we have our relationship. So you see here, we go from grams of O2 to moles of O2 using the molar mass of O2. Then we go from moles of O2 to moles of CO2 using the values in the chemical reaction. Then we go from moles of CO2 to grams of CO2 using the molar mass of CO2. Multiply and divide all of these numbers and you get 47.2 with the final unit grams of CO2. All other units cancel out, and the closing statement. Okay, the logic then, we started with grams of O2, that's what was given, 57.2 grams of O2, and because we have grams, we have to convert to moles using the molar mass before we can use the chemical reaction. Once we have moles of O2, then we can use the chemical reaction to find moles of CO2. And so we have the following thing. And then if that's what you seek, amount of CO2, then you're done. But the problem says what mass of CO2, and therefore we convert from moles to grams using the molar mass of CO2. And that was the logic. Okay. So next we have problem number 5. For the same reaction, what amount of H2O is generated if the reaction generates 9,420 kilojoules of heat? Now in this case we have an added term, 2,043 kilojoules, and this is to be interpreted in the following sense. Every time you use 1 mole of C3H8, you create 2,043 kilojoules of heat. You can also say every time you use 5 moles of O2, you create 2,043 kilojoules of heat. Same thing for CO2 and H2O. As an example, for H2O, you can say every time the reaction generates 4 moles of H2O, it also generates 2,043 kilojoules of heat. And these numbers are again related through direct proportion. So for example, if you use twice as much O2, assuming you have enough C3H8, using twice as much O2 will mean you get twice as much heat. If you get half as much H2O, then you get half as much heat. And so then the heat term is also related to the amounts through direct proportion, and therefore the approaches that we are talking about here are all appropriate. This is important, by the way. You have to make sure that you check to see that the quantities that you're dealing with are related through direct proportion before you set up your equations. Otherwise, these setups will not work. In this case, in the case of chemical reactions, we are talking about 3 quantities in these examples. Amounts, sometimes we talk about masses, and sometimes we talk about heat now. And all of these 3 are related through direct proportion, and therefore the approaches that we have are good enough. As an example, twice the amount, that's twice as many molecules, means twice the mass. And you can see here, if you use twice as many O2s, you end up with twice as much heat, and so on. All right, so now we find one relationship from the chemical reaction that relates H2O and heat, amount of H2O and heat. So in this case, we don't have two different molecules. One of them is a molecule, the other one refers to heat. And our relationship, therefore, is 4 moles of H2O corresponds to 2043 kilojoules of heat. So 4 and 2043 are the two numbers that we picked from the chemical reaction. All right, so let's start off our solution. N is the amount of H2O that is generated in moles, and then one relationship, one division. We start with the value that we want to work with, which is 9,420 kilojoules of heat, the given, and then the numbers 4 moles of H2O and 2043 kilojoules go on top and the bottom. Matching the unit in the divisor, we write down 2043 kilojoules and then on top 4 moles of H2O. We multiply and divide to get 18.4 moles of H2O and a closing statement. Right. We move on to the next problem. Oh, the logic. Yes, I forgot to tell you about that. So in this case, we start with heat, and that means we can use the reaction right away because we do have a heat term now in our reaction, and therefore, starting with kilojoules, we can use the reaction to relate this to the amount of H2O in moles. Okay, problem 6. Consider the following chemical reaction, same reaction. What mass of H2O is generated if the reaction generates 9,420 kilojoules of heat? The molar mass of H2O is 18.016 grams per mole. Now in this case, heat is given, and therefore we can use the reaction right away to find not mass of H2O, but amount of H2O, because these numbers are amounts. So we can relate heat to amount right away by using the chemical reaction. Once we have the amount of H2O, then we can find the mass of H2O using molar mass. And here then we have two relationships, and the first one comes from the chemical reaction as usual. We are relating H2O, amount of H2O, and heat, and therefore we pick 4 and 2043. 4 moles of H2O corresponds to 2043 kilojoules of heat. The next one comes from the molar mass, and this one says that 18.016 grams of H2O has a mass of 1 mole, corresponds to 1 mole of H2O. Now, two relationships, we have two divisions, beginning with what we want to work out, 9,420 kilojoules of heat. And we match the unit. Now we are using the values in the chemical reaction to relate kilojoules to moles of H2O. These are the ones that go on top and the bottom. And the quick way, of course, is to match the unit kilojoules, and there is only one that has kilojoules, 2043, that goes down, and the value that corresponds to it, which is 4 moles of H2O, goes on top. Now this converts kilojoules, it goes from kilojoules to moles of H2O. Once we have the amount of H2O, then we use the other relationship to convert to grams of H2O. And so we put down 1 mole of H2O, 18.016 grams of H2O. And we check off the next relationship, and now we have M equals 332 grams of H2O. So the reaction generated 332 grams of H2O. The logic, starting with kilojoules, we can use the reaction right away, and that relates it to moles of H2O. Once we have moles of H2O, we can use the molar mass to get grams of H2O. Okay, we have 2 more problems to go through. Okay, problem 7 now. And this problem says, for the same reaction, how much heat is generated if the reaction uses 82.4 moles of O2? Now again, because moles of O2 are given, we have moles, we can use the chemical reaction right away, the numbers here, to find heat. And this will be a single proportion kind of a problem. Okay, so we start with E being heat generated by the reaction. Heat is a form of energy in kilojoules. And we have only one relationship relating the amount of O2 in moles to heat from the reaction. So 5 moles of O2 and 2043 kilojoules. That's our relationship. There will be only one division, and we start with the quantity that we want to work out, 82.4 moles of O2 on the right hand, and then we relate moles of O2 now to kilojoules using the values in the chemical reaction. Matching the units, moles of O2 goes down and kilojoules goes on top. So 5 moles of O2 and then 2043 kilojoules. This gives us 33,670 kilojoules of heat. Okay, I'll let you work out the logic yourselves. And we move on to the next problem. Problem 8, which is the last one, says for the same reaction that we have been working on, how much heat is generated if the reaction generates 52.9 grams of H2O. The molar mass of H2O is 18.016 grams per mole. Now again, this time grams are given, and therefore we cannot use the reaction right away because reactions deal with moles only. So we have to convert from grams to moles. That's why we need the molar mass of H2O. Once we have moles of H2O, then we can use the reaction to find out how much heat we get. There will be two relationships in this case. One comes from the reaction, which is relating amount of H2O to heat, and that's 4 moles of H2O and 2043 kilojoules of heat. The other one comes from the molar mass. 18.016 grams of H2O corresponds to 1 mole of H2O. Okay, two relationships, two divisions. Beginning with what we want to work out, 52.9 grams of H2O. Now we convert from grams to moles in order to be able to use the values in the chemical reaction. That's where the molar mass comes in. Again, we match the unit, grams of H2O. So 18.016 grams of H2O goes down and 1 mole of H2O on top. Now that we have moles of H2O, then we use the other relationship which comes from the reaction to find heat. Matching the unit, 4 moles of H2O goes down and 2043 kilojoules goes on top. This gives us 1500 kilojoules of heat. Okay, I leave you to work at the logic. Don't forget, if you want to make sense of why is it that the setup here works, you can always do your divisions, find unit rates, and then interpret going from right back. And don't forget, you can also interpret from going left-right. That's a very interesting kind of interpretation as well. Okay, I believe that brings us to the end of this video. And thank you so much again, as usual, for watching. I'll see you in the next video. And until then, I will be gone in 3, 2, and 1, with a bit of delay, perhaps. Or not showing at all.